G'day, g'day. Welcome to Lab Suite Lab. This is one of the plasma physics laboratories at the School of Physics in the University of Sydney. We like to call it the ARC Lab for reasons that will soon become apparent. In this lab, we have some pretty interesting pieces of equipment, such as this guy. This is a pulsed cathodic arc plasma source, and today I'll be walking you around this fella and showing you how the system works. Firstly, let's take off this copper box. Firstly, it's made out of copper so that if there is any inadvertent contact between any of the power connections and the box, it can be earthed safely. When the system charges up, there are anywhere between 50 and 400 volts between cathode and ground. We need to make sure we operate this machine safely because I don't want to die while I do my work. Inside the box, let us not dwell on that, inside the box we have some fairly chunky power connections. We also have cooling water connections so that we don't have the cathode melt inadvertently. We also have some data connections. This is a voltage probe connection. This is a Rogowski coil. It measures how much current goes through these two cables. We also have this guy here. That's a safety interlock switch. If the box is open, it earths the main capacitor bank, making sure that we're as safe as we can be. So in order for it to charge, the box has to be closed. So if you want to come around a little bit further, I will show you how our thrust measurement system worked. We've taken away one of the big mirrors so you can see everything a little bit more easily here. There's ordinarily a large mirror here that'll bounce the laser beam from this laser down through this portal and into the chamber. Inside the chamber at that location, we have this guy. This is my ballistic pendulum. Well, one of my ballistic pendulums. One of the things I use to measure thrust. If you notice at the back, there's this little grating here. When it's hanging nice and still like this, the laser beam will go straight down through the grating and bounce off a mirror and come back up and then go off to a sensor. As the pendulum gets hit by the plasma, however, the pendulum will start to swing. As it swings, the grating lines will interrupt the laser beam, which will get registered on our sensor, which is this little photodiode here, right in the middle. You get registered on the sensor as a change in intensity of the laser beam. With that changing intensity being plotted as a graph on an oscilloscope screen, we can then determine how fast our pendulum is moving and therefore how much thrust the system is producing. The system actually looks pretty interesting as well. If you come around a bit further, you can have a look through this big glass window there, and you can see the coil and you can see the anode. The coil is there to function like a rocket nozzle. You can't use a rocket nozzle made out of material stuff like ceramics or steel because the plasma would hit the rocket nozzle and stop. It would just plate it, wouldn't do very well. So we're using magnetic fields to do the job instead. The big hollow cylinder you saw was the anode. You can't see the cathode as it is right now because the cathode's currently being shadowed by the anode. You'll be able to see some plasma in a moment, specifically titanium plasma because there's a titanium cathode in the system. But first, let's show you some more of the power supply. Inside this big cabinet here, we have the main power supply bank. You can see a range of electrical components. We have some capacitors, some inductor banks, and the main bank is the one right down at the bottom there. Each half bank contains about 21 millifarads worth of capacitance. So there's a fair amount of storage of energy there. When we drop the switch and this arc starts, several thousand amps go through the plasma discharge in less than half a millisecond. So all the various high current warning signs, they're there for a reason. All the various safety switches, like this one here, are also there for a reason. Let's keep going around, I'll show you some more. So this is the front of the power supply section. We have the main switches on this board here. We're going to turn on the main bank, start charging it up. You can hear the fans and the cooling system starting up. The main bank is charged to 200 volts, and we're not using the duct or the substrate systems at all. They're not just not being used for this experiment. We can switch them in for other things. We're opting not to use them. Also, the substrate is currently switched out to be safe. It's currently under a bit of maintenance. We can queue up some shots to fire. I've done that already. I've got 50 shots, and away we go. Now, if you come back around with me, we can have a look back through that window, and we should be able to see a lot of plasma. And yeah, and it looks beautiful. That beautiful blue glow, that's titanium plasma. Those are titanium ions recombining with electrons in the plasma and emitting light. Under these current conditions, according to my measurements, those ions and those electrons, the entire plasma, is moving at about 60 to 70 kilometers per second as an average effective velocity. Our rocket works by making exhaust material move in one direction really fast and using conservation of momentum to get pushed in the other direction. That's how my system works as an arc, and this is how my system works as a rocket. Thanks for coming by the lab. I hope you have a great day.